Graph Convolutional Networks, GCNs, Part 5, a simple GCN. Stay tuned for more tutorials at LearnAI_CV. In this video you will learn components of a simple GCN. In this figure, you see a graph with 8 nodes. Each node has a feature vector. We are going to give an example of computing a GCN layer for this figure. A multi-layer perceptron layer consists of a linear and a non-linear function. A GCN layer has one more component, an aggregation function. Feature aggregation distinguishes between an MLP and a GNC. At the beginning of each layer, the information from neighbor nodes is aggregated. A GCN layer integrates the graph topology and features of the nodes in a local neighborhood. A multi-layered perceptron can have L number of hidden layers between the input and the output layer. The first hidden layer takes input from input layer and process them using activation function and pass them to next hidden layers until output layer. Graphs in the real world contain rich information that cannot be extracted from individual nodes alone, but the connections between nodes include an important part of the information. In order to analyze the information from a graph, the designed architecture must capture underlying relation which cannot be inferred from the node features. Graph Convolutional Networks, GCNs, are proposed to analyze graphs based on the individual node features and the structure of the graph. A general GCN layer is composed of two main components, an aggregator and a neural network. The aggregator component aggregates the information from the neighbor nodes, and the neural network updates the representation of the node. Consider node V0 in the figure. We apply a simple GCN model to this node. As you see, node V1, node V3, node V5, and node V6 are the neighbors of the node V0. The first component of this simple GCN is the aggregation function which aggregates the information of the neighbors. In this example, the aggregation function is the sum function. So, we compute the summation of the features of the neighbor nodes. The second component of this simple GCN is the linear function which multiplies a weight matrix by the result of the aggregation function. In this example, the weight matrix is a matrix with 2 rows and 3 columns of random weights. The third component of this simple GCN is to apply a nonlinear function to the resulted vector. In this example, we apply the rectified linear unit as the nonlinear activation function which is defined as the non-negative part of the argument. The summary of the whole process is shown in this formula. First, we sum up the features from neighbor nodes. Then, we multiplies a weight matrix by the result of the sum. Finally, we apply a nonlinear function to the resulted vector. This formula shows the general idea of all GCN models. All GCN models consist of 3 main functions, the aggregation function, the linear function, and the nonlinear function. The aggregation function aggregates the information from the neighbors of each node. Now, we want to show the schematic of a 2-layer GCN for node V0 in this graph. First, we find the neighbors of node V0. Nodes V1, V3, V5, and V6 are the neighbors of the node V0. The neural network in this schematic is the linear function and the nonlinear activation function. Now, for computing the second layer of the GCN, we have to find the neighbors of the neighbors. For example, nodes V0, V2, and V7 are the neighbors of the node V1. We again apply an aggregation function and a neural network to the neighbors of the neighbors. This part of the network shows the first layer that aggregates the neighbors of node V0. These neighbors are called the first hop neighbors of the node V0. This part of the network shows the second layer that aggregates the neighbors of the node V0. These neighbors are called the second hop neighbors of node V0. The design of neural network, the aggregation function, and the selection among neighbor nodes distinguish one architecture of GCN model from the others. Stay tuned for more tutorials at LearnAI_CV. Graph Convolutional Networks, GCNs, Part 6, the role of adjacency matrix in GCNs. Stay tuned for more tutorials at LearnAI_CV. In this video you will learn adjacency matrix, degree of a node, degree matrix, normalized adjacency matrix, and walk. In this figure, you see a graph with 8 nodes and its adjacency matrix. Consider node V0 in the figure. As you see, node V1, node V3, node V5, and node V6 are the neighbors of the node V0. So, the corresponding elements will be 1. The adjacency matrix, sometimes also called the connection matrix, of a simple graph is a square matrix with rows and columns labeled by graph nodes, with a 1 or 0 in position Vi, Vj according to whether Vi and Vj are neighbors or not. For a simple graph with no self-loops, the adjacency matrix must have zeros on the diagonal. For an undirected graph, the adjacency matrix is symmetric. The degree of a node is the number of its neighbors. In this figure, you see D0 is 4, D1 is 3, D2 is 1, D3 is 2, D4 is 1, D5 is 2, D6 is 1, and D7 is 2. The degree matrix of a graph is a diagonal matrix in which the diagonal elements indicates the degree of the nodes. The degree of a vertex can easily computed just by taking the sum of the values in either its respective row or column in the adjacency matrix. In the previous video, you saw that GCN models consist of 3 main functions: the aggregation function, the linear function, and the nonlinear function. The aggregation function aggregates the information from the neighbors of each node. In a simple GCN, the aggregation function is a sum function that sums up the neighbor features. This formula can be represented by the adjacency matrix. Consider node V0 and V2 in the figure. We apply an aggregation function to these nodes. As you see, aggregation at node V0 results large values because it has more neighbors and a larger degree. A vertex with a large degree dominates the other vertices with smaller degrees. Normalization is applied to make the influence of all vertices more equal to each other. Normalized adjacency matrix is defined as follows. We need to calculate the square root of the degree matrix and then multiply it once from the left side and once from the right side in the adjacency matrix. Now, you learn how to compute the power of a degree matrix, which is a diagonal matrix. You also need to learn how to multiply a matrix by a diagonal matrix. What is the result of pre-multiplying a matrix by a diagonal matrix? The result is that of multiplying the row I of matrix A by the factor ki. The successive rows of the original matrix are simply multiplied by successive diagonal elements of the diagonal matrix. What is the result of post-multiplying a matrix by a diagonal matrix? The result is that of multiplying the column I of matrix A by the factor ki. The successive column of the original matrix are simply multiplied by successive diagonal elements of the diagonal matrix. For computing the power of a diagonal matrix, we must compute the power of the diagonal elements. In normalized adjacency matrix, the aggregation is divided by the square root of the destination and source node degrees. A walk on a graph is a sequence of edges which joins a sequence of nodes. In this graph, there are 8 walks starting at node V0 with length 2. There is theory which says the element ij of a to the power of n equals to the number of walks with length n from node I to the node j. In this figure, we compute the adjacency matrix to the power of 3. The element in the first row and the second column shows the number of walks from node V0 to the node V1 with length 3. You see the list of walks in the right side. Stay tuned for more tutorials at LearnAI_CV.